Now, we're going to talk about a little bit of terminology because the vector computing uses a slightly different language than regular computing. And one of the first things we're going to talk about is this idea of a vector register. Now, a vector register, we've already kind of talked about. It's one of these huge, long registers. And it's got lots of bits, 128, 256 bits. So those bits, though, the thing that's nice about those bits is that they can be divided up into pieces, just like we talked about with AL and AH and E and AX and EAX. This is not that different, except that what you're going to do is you're going to load a single vector. So I had like this A sub 0, A sub 1, A sub 2, A sub 3, and so forth. Now, in doing this, I can have a multiple elements inside of a single, and it's referred to as a register, but that term register may be misleading because really what we're looking at is, in this case, my single register has been divided up so it's carrying 4 array elements. All right. Now, those 4 array elements could be combined with 4 more array elements in a different vector. So this one's maybe R0, this one's maybe R1, and in this one we could have B sub 0 and B sub 1 and B sub 2 and so forth, right? And by doing this, now what I have created is something a little bit different. You notice that each one of these registers are kind of, the elements of these registers are all lined up. And that line is going to be what we're referring to as a lane. So when an operation is performed, let's go ahead and say we're going to create a destination register. So I've got R2 here, and it's also being divided up into its pieces. And what we're going to do is we're going to put A sub 0 plus B sub 0 in the first column, and then A sub 1 plus B sub 1 in the second portion of that register, A sub 2 plus B sub 2, and then A sub 3 plus B sub 3. And so when we perform an addition, what's going to happen is B and A are going to get added together in order to put the result in that first portion of the register. There is not going to be any interactivity between the registers. And then whenever that same operation occurs, when we do that add, we're going to add those registers together in order to put it in the second slot. And then we can also have the registers from the third quarter of these vector registers R0 and R1, putting a result in the third element of R2. And then we can also have B3 and A3 added together in order to go into the last element. Now, the thing that makes this parallel is that these guys, that is actually going to be a single instruction. One instruction. Ran out of room. One instruction. And so when you so we're going to load the vector registers with their pieces. We're going to do the single instruction, just say add vectors, it'll add it. You have to tell it the size because remember, these vector registers could be broken up into a different size if we're talking about 8-bit elements instead of 32-bit elements. But we add those together, no interaction. Carries are going to be handled slightly differently. We'll talk about that in a minute. Now, as I said before, this kind of column of registers, this is referred to as a lane. And so whenever I'm talking about a lane, what I'm talking about is, for example, if I were to add, imagine that we had this instruction with Intel. Add vector EAX to vector EBX. And whenever those were added together, we were able to do it 8 bits at a time. And so the first 8 bits were added together for a result, no carry into the next 8 bits. And then the next 8 bits were added together in order to get a result in the next 8 bits. Each one of those columns of 8 bits being added together, that's referred to as a lane. So we got 2 definitions here. We have vector register and we have lane. Let's go on with another definition here. And this one's a little bit, I will show a good example whenever we start talking about the ARM processor, but this idea of interleaving. Interleaving doesn't have anything to do specifically with the vectors themselves. It has to do with the loading and storing of the vectors to memory. So think about having your, let's say that I have stereo data. In other words, I have in memory data, and I don't know what's going on graphically here. And so I have the left channel and the right channel for sample 1, for sample 0. And then I have the left channel and the right channel for sample 1. And then I have the left channel and the right channel for sample 2. Left and right for sample 3. And then left and right for sample 4. Now, when I want to manipulate the data, let's say that I want to do some sort of a process, or perform a process on the data. Typically, what I'm going to do is I'm going to grab the left data. And if I want to do some sort of a digital signal processing, it's going to treat that as a single audio stream. If I included the right channel in that stream, you would get incorrect data because these are 2 audio streams, one that goes into the left ear, one that goes into the right ear. And so whenever it comes to, whoop, didn't mean to do that. Where am I? And so, there we go. So then I'd have in a separate operation the data for the right channel. Well, if it's stored linearly like this in memory, I have to have additional capability of my assembly language instructions to separate this data. Well, that's what interleaving is. Interleaving says that I can have interleaving of 1, 2, 3, or 4. And this means that if I'm loading one of my registers, one of my vector registers, let's say that I'm trying to load my left channel, then what I'm going to do is I'm going to have an interleaving of 2 so that I grab the first left value, then the next, sorry about this. First grab the first left element, then grab the next left element, then grab the next left element, then grab the next left element. Notice that I am skipping over. An interleaving of 2 basically means I'm going to load every other memory element into my register. Now this doesn't have anything to do yet with the size of the data. For example, if I have 16-bit values that I am loading for left register values, that's going to be handled with a slightly different mechanism in our instructions. Interleaving of 3, real good with RGB data, right? So I have red, green, blue. I can load all the red values into one vector register, all the blue values into another vector register, and then all the green values into another vector register. Remember the example from earlier on when I took all 3, red, green, blue, added them together and then divided them. Interleaving of 3 would help me with this, because then what I could do is I could use an interleaving of 3 and load one vector register with all the red, load one vector register with all the blue, and load one vector register with all the green, and then add them together as 8-bit vector values. Get a result, do a division, and perform and then have my grayscale. Okay. And interleaving of 4 gives us the ability to add in that fourth element whenever it comes to graphics that we use for alpha. All right. All right. I think that's where I'm going to stop it. We'll hold on to the next topic for the next video.